everyone, this is Miss Ward. Tonight your notes are going to be in Motion in Two Dimensions Unit Concept 6. It's going to be more of that non-horizontal projectile motion. Just going into it a little bit more in your notes. We've already done a lot of this in class. And then we're going to end it with an example problem which is a little different than ones we've done in class, just to show you how you can do the same kind of problem but with a little bit different strategy and thinking out of the box a little bit. Okay, so this notes are focusing on the angles when we talk about non-horizontal projectile motion. So as we know, projectiles don't always start off in the horizontal direction. They can be launched in any direction and at any velocity. We use the trig functions to find them. Generally, the initial velocity of x is equal to the initial velocity of the object times cosine of theta, and then the initial velocity of y is equal to the initial velocity times the sine of theta. And these just come from the idea that in our triangle, if this is our velocity, hold on, I'm going to move that down here. These just come from the fact that if this is our triangle, alright, and this is our initial velocity in general, this is initial velocity of x, this is initial velocity of y, then use angle theta, and the sine of theta is equal to opposite over hypotenuse, so over VI, multiply both sides by VI, you get VI times, the sine of theta equals initial velocity of y. In the x direction, it's cosine of theta equals initial velocity of x. Something we've done a bunch of times. It's just showing you written in a slightly different way, or slightly abbreviated way, I guess you could say. So that you get the initial velocity times cosine of theta equals initial velocity of x, and initial velocity of the sine of theta equals initial velocity of y. And that's just what they show you down at the bottom, just in the abbreviated form. So then they plug those into our motion equations, where you substitute in for velocity the initial velocity times cosine in the x direction, and then the initial velocity times sine in the y direction. Remember, these are the motion equations in which they've split up our x displacement into final and initial. It's the same as when we write it. Delta x equals the initial velocity of x times time, because remember that second half of the equation, the plus 1/2 acceleration times squared, that piece cancels out. Generally, we are used to writing this instead of delta x, we generally write it as a d equals initial velocity of x times time. That's the same thing they've written there. As well as in the y direction, they're just substituting in a delta y with a y final and y initial. Normally we substitute that in with just a d. And then the initial velocity of y, they're just showing you with the pieces pushed in like that. So don't let the form confuse you. So here it is, just showing you those equations again. These are just that displacement equals initial velocity of x times time plus 1/2 acceleration times squared, and then the initial velocity of displacement of y equals initial velocity of y times time plus 1/2 acceleration times squared, just shown in a slightly different manner that is abbreviated. Alright, so let's look at this example. This is a different example than what we've looked at before. It's the same type, but we're going to approach it slightly differently, just to show you guys that there is some different ways to do these problems. So, chipping from the rough, a golfer sends the ball over a 3-meter high tree that is 14 meters away. The ball lands in the green, of course, at the same level at which it was struck, after traveling a horizontal distance of 17.8 meters. In A, if the ball left the club at an angle of 54 degrees above the horizontal and landed the green 2.24 seconds later, what was the initial speed? And then B, the ball passes directly over the tree at 1.76 seconds. How high was the ball at that time? So let's draw this out. So let's draw this out so we can see what it looks like. The way they word this problem is a bit confusing, so I want to make sure we clarify that. Here we have our tree, and they say that the ball is chipped over the tree. The tree is not at the middle point, so that 3 meters is not the highest point. That 3 meters they give us in the problem really doesn't mean anything. It tells us that this is 14, but again, that 14 doesn't really mean a whole heck of a lot. That whole total distance is 17.8 meters. That's what's the important part. And they tell us this is a 54-degree angle, and they want us to solve for what the initial velocity is. So we're looking for the overall initial velocity. Alright, they don't give us a whole lot of information, so instead of drawing my table first, because my table is basically empty, I'm going to go about trying to solve for my initial velocity of x first. I do have enough information to solve for the initial velocity of x. I can use my equation, my displacement equals initial velocity of x times time plus 1/2 acceleration times squared. The displacement of x is that 17.8 meters that they gave us, equals the initial velocity of x, which is what I'm solving for, times the time of 2.24 plus 0, because that acceleration in the x direction is going to cancel that whole section out. So I just divide both sides by 2.24, and I get that the initial velocity of x is 7.94. That's all I need to be able to solve for my overall initial velocity. All I have to do is draw my triangle. This is 7.94. This angle here is 54 degrees. So all I have to do is use my function. So the cosine of 54 equals 7.94 divided by initial velocity, multiply each side by initial velocity, and then I have initial velocity times the cosine of 54 equals 7.94, divide both sides by cosine of 54, and I get the initial velocity equals, where's my answer there? 13.5 meters per second, and they give everything to us in 3 significant figures, so that's what we're going to use. Now, in order to solve for the displacement of x, which is what they want us to know, in this letter B they're asking how high is it when it travels with the tree. So what is the height of the ball right there? We know the tree is 3 meters, but this height has to be taller than 3 meters. They want to know what that height is. The only way to solve for that is using our distance equation. Displacement equals initial velocity times time plus 1/2 acceleration times squared. They give us the time. We can solve for initial velocity using our triangle. We plug it all in, and we can solve for our displacement. If this is our triangle, this is 54 degrees. This is 7.94. I'm going to use my tangent function in this case. So tangent of 54 equals initial velocity of y over 7.94. Multiply both sides by 7.94. You should get that the initial velocity of y equals 10.93. Then I just plug that into the equation using the new time they give me. Distance equals 10.93 times 1.76 plus 1/2 negative 9.81 times 1.76 squared. When I solve all that out, displacement ends up being 4.04 meters. So the ball was 4.04 meters high, which makes sense because the tree was 3 meters high. We know it had to be higher than that. So that gives us our answer. Alright, that's it for tonight. These notes hopefully were pretty simple for you based off the fact that this is just a little review of what we've been doing in class already. Make sure you go online and do your WISC, and don't forget to start working on those practice problems because this unit, we're taking our test on Monday, Tuesday, so your practice problems for all of your units need to be done before then. Alright, have a great night.